Welcome to Chapter 8A PowerPoint. Again, there's going to be a Chapter 8A and a Chapter 8B PowerPoint. This is the chapter where we explain the general circulation of Earth's atmosphere, the strong rivers of air in the upper atmosphere that we refer to as jet streams, and winds that are extreme and not so extreme, local wind systems. Here is a picture from the Chapter 8 cover, the beginning of Chapter 8, of high winds sweeping dust into the air in May 2005 near Arnold, Nebraska. The general circulation of the atmosphere is caused by unequal heating of Earth's surface. You know that Earth is tilted 23.5 degrees in the plane of the ecliptic, and that's why we have seasons. Land is heated up differently than water is. We talked about how water has a specific heat, just 3 times hotter than, more so than land. And so we've got this unequal heating going on. Obviously, the tropics experience a net gain in solar energy, while the poles experience a net deficit of incoming solar radiation. The atmosphere and the ocean currents work together, but mostly the atmosphere, transporting warm air poleward and cold air equatorward. The first model that kind of explained this was proposed by an English meteorologist in the 1700s by the name of George Hadley, who devised what he called the single-cell model of atmospheric circulation, which assumes that Earth's surface is uniformly covered with water, the sun is always shining directly over the equator, and that the Earth does not rotate on its axis, i.e. no Coriolis. These conditions obviously don't exist. The spinning Earth, along with uneven heating, produces in reality a 3-cell model. The figure on the right there, 8.1.a, shows Hadley's theory of global circulation, where warm air would rise at the equator, travel in the upper atmosphere, sink and become cold at the poles, and then travel down to the surface toward the equator and become warm again during that journey. Made a lot of assumptions about Earth's system. The 3-cell model, and we know this exists now because we now have modern weather observations at airports to confirm this from all over the world now for, a good 100 years or so, ever since the advent of aviation, essentially. This model does assume, even though it is closer to reality, that Earth's surface is still uniformly water, but this is pretty close to reality. We have wind belts that have names, the doldrums, the subtropical high-pressure systems, the horse latitudes, the trade winds, intertropical convergence zone, the westerlies, that was what we essentially experience here, the polar front, which comes down to our area sometimes in winter, the subpolar low, which sometimes comes down to our area in winter, and the polar easterlies, which are those very cold easterly winds over the North and South Pole. These are the names of wind systems which you will study in more detail as you, of course, read the chapter, which we do not have the luxury of time to go over in great detail here, each individually. But this is the general 3-cell model of the circulation of the atmosphere. In honor of Hadley's big idea, meteorologists have named the Hadley cell the cell of circulation from 0 to 30 degrees north and south latitude, either side of the equator. The middle cell is where we live. That's between 30 degrees and 60 degrees latitude on either side of the equator, north and south. Sometimes it's called the Ferrel cell, after a 19th century American meteorologist by the name of William Ferrel. No, not the actor, not Ron Burgundy Anchorman, okay, different guy. And then there's the polar cell, 60 degrees to 90 degrees latitude on either side of the equator, which is self-explanatory. So it's a 3-cell circulation, which is much closer to reality. We're going to take a look at semi-permanent high-pressure and low-pressure systems to give you an idea of how things operate on the average. There are semi-permanent highs and lows that move slightly during the course of the year following the seasons. These belts of pressure and temperature tend to follow the high sun angle. They go to the northern hemisphere during our summer and then shift southward to the southern hemisphere during their summer, July and January, respectively. In the northern hemisphere, the Bermuda high pressure and the Pacific high pressure are weaker and farther south in January than in July. The Aleutian low pressure and the Icelandic low pressure are stronger in January than in July. The Siberian high pressure and the Canadian high pressure, which are caused because of bitterly cold Arctic air, are on the map. They're visible in January, but you don't find them in July. They're replaced by low pressure systems, thermal lows that are caused by heating of the deserts of North America and Southwest Asia. And that, of course, is all, as I just mentioned, due to the heating in summer. So now we're looking at the average surface high and low pressure circulations in January. The red line connected with those lows near the equator is called the intertropical convergence zone, a line where a lot of thunderstorms occur on a daily basis. This is the pattern for January. Now, please focus your eyes on the screen as I shift from January to July. Hopefully this will be a dissolve effect. But I want you to see how everything shifts northward in northern hemispheric summer. You are currently looking at southern hemispheric summer. Notice the giant Siberian high because of cold air over Eurasia, and the Canadian high for the same reason over northern North America. So here we go. Here are the January patterns, and here are the July patterns. You can see how the high pressure over the North Atlantic and North Pacific gets stronger in summer relative to the low pressures that develop over Eurasia and also the southwestern U.S. because of the intense summertime heating. So you can see how the seasons shift from south to north, January and July. Talking a little bit about general circulation and precipitation patterns, you would expect abundant rainfall to occur in areas where air rises and very little precipitation where air sinks. So there is ample rainfall around the equator where humid air rises in conjunction with the intertropical convergence zone, the ITCZ, or the equatorial low as it's sometimes called. Also, there is ample rainfall between 40 degrees and 55 degrees latitude along coastlines either side, north or south latitude, at those latitudes, where mid-latitude storms in the polar front force air upward, forces air to rise. The northern and southern fringes of the intertropical convergence zone are also influenced by the subtropical high, so they tend to be wet during high sun or summer and dry during low sun or winter. More on this. Places exclusively influenced by subtropical highs are mostly dry, the world's great deserts. Places on the northern fringe of the eastern side of those subtropical highs have wet winters and dry summers. Do you know any place that has a wet winter and a dry summer? Think about that for a minute. We'll get back to it. Places on the western side of subtropical highs, meaning the east coast of the U.S., tend to have ample precipitation in all seasons. Places mostly influenced by subpolar lows tend to have ample precipitation in all seasons, i.e. British Columbia and much of Western Europe. Places exclusively influenced by polar highs are mostly dry. The poles are the frozen deserts of the world. Okay, so back to that earlier question. Places on the northern fringe of eastern side of subtropical highs have wet winters and dry summers. What place do you know of that has a wet winter and dry summer? How about the place you live in, like Fresno? That's where we are. Here is a little study of subtropical high-pressure systems and North America. The left-hand graphic, 8.7, these are the summer positions of both the Pacific High and the Bermuda High, and the strengths of those highs. You can see the central pressure noted. Where we have dry weather in our summer because we are on the eastern side of that high, adjacent to the west coast of a major continent. That means sinking air, which is not conducive to cloud formation and precipitation. Whereas in summer adjacent to the Bermuda High, because the eastern U.S. is on the western side of that high, they have ample precipitation in all seasons. Evidence, look at figure 8.8. Compare the monthly mean precipitation for Los Angeles, adjacent to the Pacific High, and Atlanta, which is adjacent to the Bermuda High. Notice how LA has a distinct wet winter and a distinct dry summer, where in Atlanta there is ample precipitation in all seasons. Let's talk about the wind flow and pressure patterns aloft, now that we've explored the ones on the surface, above our heads. Air is warmer over lower latitudes. Colder air is over higher latitude. That's kind of a no-duh. This horizontal difference in pressure, temperature I should say, which is a temperature gradient, produces also a horizontal difference in pressure, which is a pressure gradient. That causes winds to blow from the west in the middle latitudes. The winds above our heads in the middle latitudes are called the westerlies. These pressure gradients and temperature gradients are stronger in each hemisphere's respective winter, so the winds in the upper atmosphere above our heads, winds aloft, are faster in winter. In the middle and high latitudes, these westerly winds above our heads continue to increase in speed above the 500 millibar pressure surface, which is roughly 18,000 feet above sea level. This is because the north-south temperature gradient causes the horizontal pressure gradient to increase with height up to the top of the troposphere, which is, of course, as you learned, called the tropopause. This results in rivers of fast-flowing air above our heads known as jet streams, which is, guess what, our topic after these two graphics. So here are the average upper-level atmospheric pressure patterns for January. You can see high pressure belt closer to the equator, and then you can see how this high pressure belt shifts northward in July as northern hemispheric summer takes hold, and that high pressure belt is basically stretching from the extreme southern United States, northern Mexico across to North Africa. The rivers of air above our head that travel very fast are called jet streams. They are thousands of miles long, they're a few hundred miles wide, and less than a mile thick, not very thick at all. Wind speeds in the core of these jet streams often exceed 100 miles an hour and can occasionally exceed 200 miles an hour. What this means is that on our windiest days here in the valley, that means that often the jet stream is right over the top of our head. This jet stream is usually found at the height of the tropopause, meaning where the troposphere is going in transition, high up above our heads, at altitude, say, between 6 miles and 9 miles above the surface of the Earth. The jet stream near 30 degrees latitude is called the subtropical jet stream. The jet stream near the polar front is called the polar jet stream. That's farther north than we are. Occasionally, the polar jet stream can split into two branches, and we call that the northern branch and the southern branch. When storms split apart offshore, they often have a northern branch of the jet and a southern branch of the polar jet. Jet streams, just like all winds do, form from horizontal differences in pressure, which are ultimately caused by horizontal differences in temperature. Since the temperature contrasts are stronger in winter, that produces stronger pressure gradients. That means the jet streams tend to be stronger in winter and weaker in summer. The illustration, figure 8.11, shows the approximate positions in wintertime, northern hemispheric winter, of the subtropical and polar jet streams. Here's a little bit of a cross-section of the jet streams in the northern hemisphere, stretching from the equator to the North Pole. In northern hemispheric winter, you can see the subtropical jet stream is located at a higher altitude because you have to go higher up at lower latitudes to find the tropopause, as we learned in Chapter 1. The polar jet stream is at a lower altitude because the tropopause is at a lower altitude the farther north you go toward the North Pole. Here's an analysis of the jet stream from March the 9th, 2005. The chart on the left shows the 300 millibar analysis, meaning you've gone through 70% of the mass of the atmosphere. This is way up where jetliners fly at about 30,000 feet in altitude, and you can see the winds depicted there of 125 miles an hour in the polar jet coming down from Canada, and 150 miles an hour in the subtropical jet coming in from Mexico. The right-hand graphic, 8.12b, is the corresponding satellite image, which we can also use to analyze the positions and relative strengths of both the polar jet stream and the subtropical jet stream in this case. Jet streams are important because they play a major role in the transfer of heat energy between the poles and the equator, and they're also significant in the development of mid-latitude cyclones, which is a type of storm that we're going to take an entire chapter to study later on, severe thunderstorms, and tornadoes. Now, there is also a low-level jet stream, which is frequently found in the Great Plains of the United States in the spring and early summer, coming from the Gulf of Mexico, which is instrumental in transporting moist air northward for the formation of severe thunderstorms and tornadoes in the spring in the central and southern plains. Obviously, strong jet streams can be a factor in aviation because up where those jet streams are where airplanes fly. In the vicinity of the polar front and subtropical jet stream, there can be sharp changes in wind speed and or direction, producing something called wind shear, which of course commercial and military aviators do experience from time to time. That's when the fasten seatbelt sign goes on. This can produce turbulence for aircraft, updrafts and downdrafts, cumuliform clouds, rising thermals, If you're near a jet stream in a zone of wind shear, you can get bounced around in an aircraft. These are pictures of billow clouds, figure 2, forming where the jet stream is rapidly changing speed or direction. This is the end of PowerPoint Chapter 8A.